Hello everyone. In the previous video, we have seen the derivation of Euler's equation of motion. In this video, I will discuss about the derivation of Bernoulli's equation by integrating the Euler's equation of motion. This was the Euler's equation of motion which we have already derived. dp by rho plus g dz plus v dv is equal to 0. When I integrate this equation, I'll get integration of dp by rho plus integration of g dz plus integration of v dv is equal to constant. The integration of 0 is constant. When I integrate this, rho is a constant value, so the only integration is of p, which becomes dp, which is p. Integration of dz is z, and integration of v dv is going to be v square upon 2. When I divide throughout by g, I will get p upon rho g plus z plus v square upon 2g is constant. Constant divided by another constant will again remain a constant on the right hand side. So I can rewrite this as p upon rho g plus v square upon 2g plus z is equal to constant. This equation 4 is called as Bernoulli's equation, where the terms signify p upon rho g stands for pressure head per unit weight of the fluid, or it is simply called as pressure head and its unit is meter. V square upon 2g is called as kinetic energy per unit weight or kinetic head. Its unit is again meter, and Z is called as potential energy per unit weight or potential head, whose unit is again meter. The unit of each term is meter and they are added together over here, whose value will remain constant for any section of the pipe. There is a small note: p upon rho plus g dz plus v square upon 2 is constant, which was Bernoulli's equation without dividing throughout by g. But if I multiply throughout by rho, I will get p plus rho gz plus half rho v square is equal to constant. P is the absolute pressure of the fluid, rho is the fluid density, z is the head above some reference point where your pipe is placed, v is the velocity of the fluid flowing through the pipe, whose unit is meters per second. Now, Bernoulli's equation is a form of conservation of energy, which means whatever energy is entering the system is supposed to leave the system. There is no energy created or destroyed in this format. Now, if I replace rho in the second term, as you can see over here, the second term is rho gz. If I replace it with m upon v, which is the formula of rho, I will get mgz upon v. Now, mgz is nothing but your potential energy in the gravitational form. So, this is PEG upon v, which is volume. So, rho gh term from this equation stands for gravitational potential energy per unit volume. Here v is your volume. Now again, if I replace the rho value in the third term is half rho v square. If I replace it, I will get half mv square upon capital V, which is the volume. Half mv square is the formula of kinetic energy, and this v is your volume. So I can also say that half rho v square term stands for kinetic energy per unit volume. Now, as far as the first term is concerned, which was just the term P, which is absolute pressure, we will discuss about this in a different way. P is F upon A, which is the force applied per unit area. So its unit is Newton per meter square. Now if I multiply and divide this unit Newton per meter square by meter, I am multiplying with meter and dividing by meter. So I get Newton meter in the numerator, and in the denominator I will get meter cube. Newton meter stands for joule, so it is joule per meter cube. Thus, the term P will indicate pressure energy per unit volume. Now, if you observe carefully, each term over here is indicating some form of energy. This is standing for pressure energy, this term stands for the potential energy, and this term stands for the kinetic energy. So, the summation of pressure energy plus potential energy plus kinetic energy of the entire system is going to remain constant. Assumptions made in deriving Bernoulli's equation. The fluid is idle, which means the viscosity is 0. We had taken Fv term as 0, if you remember. So the only two forces which we have considered was gravitational force and pressure force. The second one, the flow is steady. Hence we had assumed dou v by dou t equal to 0. Third one, the flow is incompressible, hence the term rho does not change with respect to time and it is going to remain same. The flow is irrotational. Irrotational basically means that while flowing, the fluid is not going to rotate about its own axis and it is going to have a linear flow. These are the four assumptions in deriving Bernoulli's equation. Now there's a small note here. We follow a small volume of fluid along its path. Various quantities in the sum may change, but the total remains constant. If you look over here, this term P upon rho g plus V square upon 2g plus Z is going to remain constant over the entire pipe flow, which means I can say that for first section, if I take this value will be equal to the summation of this value at any other section. Here we have taken at two sections, 1 and 2. So this is how you write for two sections. If you want to write for more number of sections, you have to just keep on writing. This is all about Bernoulli's equation.